We have x1, x13, x23, so on up to xd3, and this goes on up to this goes on up to 1 x1 x1n, x2n, so on up to xdn. Fine, this was your WD. This was what we formed. Fine. After that we used matrix. We said that we wanted to find, since we wanted to find y minus xw, and this may always not be possible. Not be possible to find. So we said we will find the minimum of, because this is equivalent to finding y minus xw, we will is equal to 0. We will say we will find the minimum w arg min of w such that y minus xw 2 norm is minimized. Fine. Yes. We do this. Okay, and then we use some matrix calculus methods. To do further optimization. Okay, now let us see it in some other way. So your y is equal to xw was to be solved in the optimal sense. Fine. So let us now define something called the column space of a matrix, say A. Okay, so A will be, A is say A1, A2, so on up to AM. Okay, these A1 to AM, AI are the columns of A. Fine. Now let us also define A is equal to the same A as B1 transpose, B2 transpose, Bn transpose. Okay, or say some Bk transpose. Yeah. So this will be a Bi's transpose are rows of A. Fine. This is good. Now, column space of A is, so we have this, we had this here. We define column space of A as alpha 1 A1 plus alpha 2 A2 plus so on up to alpha m AM for all alpha I belonging to R.
Basically taking linear combination.
Yeah. The linear combinations of all columns of A, of columns of A. Okay, so this is indeed the linear combination of columns of A. Fine, this is done. Now similarly, if I want to define something called the column space of A transpose, here it was, this is the column space of A. Now if I want to define something called the column space of A transpose, let me write A transpose here. A transpose will be B1, B2, so on up to Bk. Fine. So the column space of A transpose will be
linear combinations of Bi's.
Is linear combination, any linear combination of bi's. Fine, that is some beta 1 b1 plus beta 2 b2 plus so on up to beta k bk. Fine, this is linear combination of bi's. This is for all beta I belonging to R. For all beta I belonging to R. Now what we want to do is if I want to represent in notation the column space of A, how do I write it? It can be written as A times x for all x belonging to R n. Say this A was m cross k matrix, k cross m matrix. A was R k cross m. So R k cross m. So this is R m. Do you see this?
Yeah.
This is the column space of A. Okay. Why is this so? Because if A was A1, A2 so on up to AM, and this X was X1, X2 so on up to XM, then this is indeed X1 A1 plus X2 A2 plus X3 A3 plus so on up to XM AM. Since we said this X for all X belonging to RK or RM, for all X belonging to RM, we had this as the column space of A. Okay, so now let us look at this equation back. We had xw is equal to y. We want to find the best w possible. Okay, now in doing all this, we are assuming one thing: x belong to R. What was that here?
R k cross m. No, sorry. RM.
No. X belong. This capital X belong to R n cross d plus 1. N cross d plus 1. And W belong to R d plus 1. W belong to R d plus 1. Fine. Now, what can you say about XW? XW is the column space of X.
Column space of X.
Fine. Since XW is the column space of X, I want to equate XW to Y. That means find a Y, find Y such that, or not find Y, find W such that Y is in the column space of X. Fine. Now, this is only true if XW is equal to Y is solvable.
Yeah.
Now, since this may not be solvable, since this may not be solvable, what we want is, we want to change the statement to find W such that Y is nearest to the column space of X.
Yeah.
Fine. Fine. So, I want to find a y cap which is nearest to the column space of X. Okay. Now,
Yes.
let us say this is your column space of X. Fine.
Yeah.
This plane, because we can't do everything in 3 dimensions, in n dimensions, we'll assume this plane is in the column space of this plane is the column space of X. Now the origin should lie in this, because for every space origin should lie in the space.
Yeah.
Now if I wanted to represent y, the y would be the vector y would be somewhere outside, because it is not in the column space of.
Yeah.
Assuming that this is unsolvable, we see that y is not in the column space of X. So this y is outside X. So what I want to find is the nearest y cap. The nearest would here be orthogonal. Orthogonal is the nearest distance, intuitively thinking. So this is what we wanted to find. Fine. So how do we do that? We want that so what is this error vector? This error vector is y minus y cap.
Y minus y cap.
Okay. Now what do you observe from this figure? That this error vector is perpendicular to the plane, or perpendicular to the column space of X.
Column space.
Fine. E cap is orthogonal to column space of X.
Yes.
Fine. So what we can say is E cap is orthogonal to alpha 1 x1 plus alpha say x is given this way, not x1. X is given as a1, a2, so on up to a d plus 1. Say x is given this. X is in this way. So we want E perpendicular to alpha 1 a1 plus alpha 2 a2 plus so on up to alpha d plus 1 a d plus 1.
Yes.
That means E is perpendicular to a1 as well as E is perpendicular to a2 and so on up to E perpendicular to a3, because this is true for all. Since this is true for all alpha I, we can write it this way.
Yes.
So on up to E is perpendicular to a d plus 1. Fine. That means if I have something like this, I have E cap ai transpose E cap is equal to 0 for I is equal to 1, 2 up to d plus 1. Since a1 is perpendicular to E cap, a2 is perpendicular to E cap and so on up to a d plus 1 is perpendicular to E cap.
Yes.
Fine. Isn't it? Now,
Yes.
so if we want to write this in matrix notation, it is a1 transpose, a2 transpose, so on up to a, what is this, a d plus 1 transpose times E cap is equal to 0.
Yes.
That means this 0.
Yeah.
Fine. Now, what is this E cap? E cap is given as y minus y cap. So, and what is this vector here now? What is this matrix here? It is your X transpose matrix.
This X transpose.
Since this was X,
Yep.
since X was this, X transpose would be that.
Yes.
So what we have is X transpose E cap is equal to 0. And that means X transpose Y minus Y cap is equal to 0.
Yes.
Fine. Now, what we have here is Y is equal. Okay. So we have X transpose Y is equal to X transpose Y cap.
Yes.
Fine. Now, what is Y?
Y is again.
We wanted Y to be XW.
Yes.
This. So, since Y is equal to XW, we want. So we substitute this here. X transpose XW is equal to X transpose Y cap. But then, what do we know in all this? We want to find Y cap is equal to XW, isn't it? We wanted to find Y cap, not Y. Since Y was nearer to XW, Y is not equal to XW because this is unsolvable. Y is equal to XW is unsolvable. Fine, since Y is equal to XW is unsolvable and we knew Y. We knew Y. We knew Y because Y was Y1, Y2, so on up to Yn. We knew this. We had this. Since Y was not equivalent to XW, you want some Y cap is equal to XW. Fine, that is what this is. So, X transpose Y is equal to X transpose XW.
Okay, yes.
Just from here. Now what you have is X transpose X W is equal to X transpose Y.
Yeah.
Now assuming X transpose X is invertible, W will become,
So we wanted to
or W star is X transpose X inverse X transpose Y. So this is optimum W that satisfies XW is equal to Y. Fine. Now just see what is this W doing. You had your column space X and then you had Y here outside, and what are you indeed finding is some Y cap. Fine. And this Y cap was given by XW. And what is this W given by? This W is given by X transpose X inverse X transpose Y. So if you write it here, X transpose X inverse X transpose Y. Fine. Now what I want you to see is this part is called the projection operator.
Projection.
Of the space X. Okay. So if we have seen in the linear algebra way. That W optimal is equal to X transpose X inverse X transpose Y, and that X transpose X inverse X transpose Y was the projection of Y in the column space of X. Okay. So this was a second interpretation of how we saw linear regression.